right. Paulina, if you want, you can go first, and then let me work around.
All right. So I was just thinking of going through Dr. Saupe's one of the practice exams that he posted. So let me open that really quick. One sec. Okay. Is everyone able to see it? If not, just raise your hand. Okay. So exam 4, we're almost there, guys. Okay, so the first question is asking sodium and magnesium and aluminum ions are all isoelectronic too. Okay, so can anyone tell me what isoelectronic means?
Like the same elements as sodium and magnesium and aluminum?
Close. So we just have to be careful with wording. Oh, sorry. Was someone else going to say it?
Oh, I was just going to say, is it pertaining to the amount of electrons being the same?
Yes, perfect. Exactly. So it is more specifically electrons that are going to look the same as a specific element. So if we're looking at sodium, so they want the sodium ion. So when sodium becomes an ion, what charge does it adapt or get?
1+.
Mm-hmm.
1+.
Perfect. So sodium plus. And we're looking at the magnesium ion. So what charge does magnesium get?
2+.
2+.
Mm-hmm. Perfect. And finally, aluminum.
3+.
Yes, perfect. Okay, so when all of these ions gain those positive charges, we change their amount of electrons, right? So are they gaining electrons or losing?
They're losing.
They're losing
electrons.
So when sodium normally, how many electrons does sodium normally have?
11.
11, perfect. So it loses 1, and now it has 10, just like neon, right? Okay, so we know sodium is going to look like neon. We know, oh, this is weird because it's a multiple choice. Okay, magnesium, when it gains 2, it's also going to go to neon, right? And aluminum, when it loses 3, it's going to go to neon. But if you look at the answer choices, all of them have, there's 3 that have neon, but they all have something else as well, right? So let's see, if we look at neon, fluorine, and oxygen, are oxygen and fluorine isoelectronic to neon?
No.
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 Okay, so what about the fluorine ion and the oxygen ion?
Yes.
Okay, so this
Yes.
looks good. Neon and argon. Is argon isoelectronic?
No.
No.
Yeah.
Nope.
No, right? So we have to have those ions. So the correct answer for this one should be D. Because if we look at fluorine, it has 9 electrons, but when it becomes an ion, it has that negative charge. So we add 1 and it has 10, just like neon and the rest of these, right? So all of these have 10 electrons, right? Everyone good with that one?
Yes.
Any
Yes.
questions? Okay, so I'm gonna, no?
I'm sorry, I keep interrupting. I was
No.
gonna ask, is there somewhere where we could like get a copy of this? Like your questions?
So I will be, of the questions, they should be on Dr. Saupe's Blackboard. So if you go to
Oh,
the
okay.
homepage,
Yeah, if you go under exam 4 stuff, it should be there.
yes.
Thanks, Alyssa.
Yeah, you're welcome.
All right. So let me scroll down to the next one. Oh, there we go. All right. So the next one says arrange lithium plus sodium plus potassium plus beryllium 2 plus and magnesium 2 plus in terms of decreasing atomic radius. All right. So this one is going to have to do with periodic trends, right? And they want decreasing. So whenever you get one of these questions, if you have to write it out, write it out. So decreasing, which size is going to go first? Smallest to biggest?
Increasing.
When it'd be the
Increasing to
biggest,
smallest.
biggest
Big.
to smallest.
To small, yes. Good. Okay, so let's try to find the one that's going to be the biggest out of all of these. So if we're looking at our periodic table, I'm just going to kind of draw them out based on, oh, and they're also all cations. Okay, so I'm just going to draw them without their charges for now. So we have lithium, sodium, potassium, magnesium, which is next to sodium, and beryllium next to lithium. Okay, so all of these are ions, but this is like their general orientation on the periodic table, right? Okay. So how do we start? So what's the difference between just regular atoms, like the regular atoms, and the ion version of these atoms? So we know that when they become cations, right, with positive charges, they lose electrons. So since they're losing electrons, the protons that are inside the nucleus are going to have a stronger pull on those electrons that are outside, right? So what happens when protons have a stronger pull?
The radius is smaller.
Perfect. The radius gets smaller. But in this case, every single one of them has a positive charge. So that's not going to affect us too much. If we were comparing cations and anions, then that would help us. But in this case, we can kind of just think of it like they were regular ions. Okay, so what is the periodic trend as we go? Let me get a different color. Okay, so as we go down, does the radius increase or decrease?
It increases.
It increases.
Perfect. And as we go this way, based on this arrow, is that increasing or decreasing at the top?
That's increasing.
That's also
Yeah,
increasing, right?
increasing.
Perfect. So both of those are increasing. So as we're going from top to bottom, why is it increasing? Does anyone know?
No.
Okay, so the reason that it's increasing as we go from the top to the bottom is that each of these, as we go to new periods, we're adding on shells for electrons, right? Electron shells. So if we have more electron shells, our radius is obviously going to increase, right? Everyone good with
Yes.
that?
Yeah.
Okay.
Yes.
Mhm.
What about as we go from, I don't know if it's flipped on your screen, but as we go from the right side of the periodic table to the left side of the periodic table, do you know why it increases that way?
It has fewer protons.
Yes, perfect, because it has fewer protons. So each period has the same shell of electrons, same amount of shells, but we increase in the amount of protons as we go to the right. So the more protons, just like we said earlier, the stronger pull, right? So that's why it increases to the left. Okay. So based on this trend that we just talked about, how should we list them?
Oh, wouldn't K be first?
Yes, perfect. Potassium would have the biggest radius. Okay, now it's going to be a little bit trickier here. Not okay. So both of these are isoelectronic to which element? Sodium and magnesium, the ions.
Oh, neon?
Yeah, neon. Neon.
Perfect. Yeah. Okay. So we know that they both have the same amount of electrons, but since they're different elements, they have different amounts of protons, right? So whichever one has fewer protons is going to be bigger because it has less pull on them, right? So which one has fewer protons?
The sodium?
The sodium.
Sodium.
Yes, perfect. And then we do magnesium. And then same thing would apply up here. So we would have lithium, right? It has fewer protons, so it's going to be bigger. And beryllium. Everyone good with that?
Yeah.
Yes. Yes, ma'am.
Cool. So the correct answer should be this one. Oh, wait. Just kidding. That one doesn't have it. K and A. It's actually none of the above. Okay. Let me, yeah. I'll share it really quick. Okay. So let me clear my screen. And let's go to the next one. Okay, so the next one says, trying to move our pictures out of the way. All right, so the next one says, magnesium, sulfur, oxygen, potassium, calcium, and aluminum are arranged in order of increasing atomic radius would be. Okay. So same thing here. Let's look at their orientation based on the periodic table. So we're looking at atomic radius again, but this time we want increasing. So this time we're going to go from small to big, right? All right. So we have magnesium, it's over here. We have sulfur in the same period, right? We have oxygen on top of sulfur. We have potassium over here. We have calcium here. And finally, aluminum, like right here. 1, 2, 3. Okay. So we just talked about this trend. So can you guys tell me which way I should draw the arrows for it to be increasing? So from top to bottom, should I draw the arrow down or up?
Down.
Down.
You want it to be down?
And then on the top, should I draw it left to right or right to left?
Left to right.
Yeah, left to right.
Right to left?
Right,
Going to the left?
right to left, right? This way?
Oh, right.
Yes, perfect. Okay, so our radius increases right to left and then top to bottom. Okay. So now that we know that, how are we going to put these in order?
Oxygen would be first.
Yeah, oxygen will go first.
Because this time we want the smallest.
And then it would be sulfur,
So yeah, sulfur. And then aluminum.
aluminum,
Perfect.
and then magnesium, calcium, and then
calcium,
potassium.
and then potassium.
Yes, perfect. So let's see if that's an option. O, S, A, L, and G, C, A, K. Perfect. That one should be D. Okay, so that one is really similar to 3. Any questions?
So you just basically look at like the periodic table and see like where they're placed.
Yes, exactly. So this is all periodic trends. So periodic table will be your best friend here. All right, let's move on. Okay, so this one is talking about the elements gallium, fluorine, sulfur, francium, and cesium arranged in order of increasing first ionization energy would be. Okay, so this one is talking about ionization energy. Can anyone tell me what that is? Okay, so ionization, we talked about ions. You know, ions have charges. So ionization, that probably means like making something an ion, right? All right, so ionization, first ionization energy is the energy it takes to remove that first electron and make something an ion, okay? So if we're looking at gallium, where is it? 31, okay, gallium is number 31. And then we have fluorine, we have sulfur, francium. Well, francium's like way over here. Okay, and cesium. Yeah, some of these take a minute to find because we don't use them that often.
It's on top of francium.
Yeah,
Oh my,
it's on top of francium.
thank you guys. Okay, cool. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool. All right. So if we're looking at this is like our compacted periodic table, right? These are the ones we care about. So we want to look at the ionization energy it would take, right? So what would be the energy to make cesium an ion? So cesium wants to become cesium plus, same with francium, right? So all of these are essentially going to lose an electron, right? They're all going to become, you can think of it like this. Now, essentially all the elements, when they're losing or gaining electrons, what do they want to become? Like, what's the ideal type of element that they want to become, or like electrons that they can have?
Like a noble gas?
Yes, like a noble gas, exactly. So cesium and francium, when they get that plus, or when they get that plus charge, when they lose an electron, do they become like noble gases?
Yes.
Yeah, they do. Yes.
Right? So they really want to lose that electron. It's super easy for them to lose that electron because they're like, yes, take it. I want to be just like a noble gas. But fluorine over here, if it loses an electron, it just becomes like oxygen, right? And it moves it further away from noble gas configuration. So it's like, oh, heck no, like you better not take an electron away from me. I want to keep all my electrons. So the energy that it takes for fluorine, like to remove an electron from fluorine, do you think it's going to be higher or lower than cesium and francium?
Higher.
Higher.
A lot higher, right? Okay, so if we want to compare the first ionization energy, it's going to increase this way and increase this way. Okay. So we can see that it's harder to think about it like between gallium and sulfur. It's hard to like make comparisons, but especially like the ones in group 1, you can tell that those really want to lose that electron. So then you can compare it to the ones that are further over. Okay, so they want increasing. So this one is small to big, right? All right. So which one should I write first?
Francium?
Francium, yes.
Yeah, francium. It'd be francium.
So francium, and then cesium, right?
Yeah.
Yes.
Gallium,
Gallium.
fluorine. Okay, cool. So let's see if that's an answer. Francium, and that's not an answer. Oh wait, oh, he messed up right here. Why did he put AS?
Yeah, that's what I was gonna ask. I had
So,
a question about that.
yeah.
Like, why does it say AS?
The answer key says B, so it must be a mistake.
Okay,
Oh, okay. I was like, what?
okay, yeah. Then there we go. Okay, cool. So it should be B. I don't know why he put AS. He just had a little fluke there, but that would be right. All right. So any questions about that one?
No. So the AS is actually supposed to be an S, right?
Yes. Mhm.
Okay. Okay.
Yeah. So no worries about that. Right, number 6. This one says the 5th ionization energy for beryllium should be. Okay, so right now we were just comparing first ionization energy level, right? So to make something just to lose 1 electron, it just gains that +1 charge. But if we want beryllium to lose an electron 5 times, let's compare that to the 4th one. Yeah, they're comparing the 4th one. So beryllium is number 4 up here. Oh, okay. So let's think about this. Beryllium is number 4, so that means it has 4 protons, 4 electrons, right? So can it have a 5th ionization energy?
No, it cannot.
No, right? That can't happen. It can only lose an electron 4 times. It can only lose as many as it has. So it does not exist. All right. And number 7. Of the following solids, which would have the greatest lattice energy? All right. So lattice energy, you're going to want to look at the charge that each of these has and the size, I believe. Okay, so for potassium, what charge does that element get when it becomes an ion?
Minus.
Okay, close.
Plus?
The opposite, right? +1.
Yeah, B plus.
And then fluorine has -1, right? Fluorine has -1 here. And lithium has +1 as well. Calcium has what charge?
+2.
+2.
Plus 2.
+2. Oxygen has,
-2.
Minus 2.
and magnesium has +2, -2 for oxygen. Okay, so the greatest lattice energy is always going to be, you want to look at which ones have the greatest charges. So from here, we can already cross out KF and LIF. So we're going to be looking at CaO and MgO. Okay, so we're essentially comparing, both of them are bonded with oxygen. So we're essentially, let me move my pen. We're essentially comparing calcium and magnesium, right? Now let's think about how we talked about radius earlier, right? So we said that the proton, like the more protons, the stronger pull it had. So that radius was smaller, right? So we're going to use essentially the same reasoning here when we compare calcium and magnesium, because whichever one has the strongest pull or like the smallest radius, it's going to be able to fit together better and have a stronger pull, right? So
Yeah.
which one has the smaller radius, calcium or magnesium?
Magnesium.
Calcium. Oh. Yeah,
Magnesium.
magnesium. Yeah.
Yeah, B magnesium.
Yes, so it's going to be magnesium. So MgO will have the greatest lattice energy. Okay. And that's just because what lattice energy is looking at is like when you think of like a crystal lattice structure, like whichever one is going to be more compact and fit tighter together and have the strongest pull to each other. So first you look at charge and then you look at essentially like radius size. Okay, any questions about that one?
No, I think it's pretty simple.
Okay, cool.
So the bigger if it's bigger, it has a greater lattice energy?
If it's smaller.
Oh, smaller, okay.
Yeah, because here we were comparing magnesium and calcium, and we know that magnesium is smaller, right? So
Yes.
I think maybe it might be confusing because calcium has more protons, but remember that calcium moves into that next period, so it has more electron shells, so that makes it bigger.
Thank you.
Okay. So let's look at number 8. Of the following solids, which would have the highest melting point? Okay, so this is going to go hand in hand with crystal lattice, essentially, or the lattice energy, sorry. So whichever one has the strongest lattice energy is going to be the one with the highest melting point, because their bonds are going to be so strong, right? That it's going to take a high temperature to melt them. So you can think of this with the same trend in the same way. So lithium, we said, has a +1. Chlorine has a -1, +1. Chlorine has -1, +1. Bromine is -1. Okay, well, all these are comparing lithium. And then finally, we have cesium down here. Okay, so all of these have the same charges. So that's not really going to help us. And then we're comparing essentially all of them with lithium, except cesium. Cesium we can cross out right away because it has the biggest radius, right?
Yeah.
Okay. So now what we're going to compare, we have fluorine, chlorine, bromine, and iodine. So do we think, essentially we're comparing fluorine and iodine, right? Because those have the biggest changes. So do we think fluorine is going to have the highest melting point or iodine?
Fluorine?
Fluorine.
Fluorine.
Yes, perfect. Because it has, again, the smallest radius, right?
Yes.
Perfect. Okay, so yeah, be mindful of that. Sometimes they will give you all of them with the same charges, so then you'll just have to move on to the next way you can figure it out.
So is that like generally the process that the charge triumphs the actual size when
Yes.
we're looking at them? Okay.
Yeah. So charge can help you narrow it down usually, and then you'll have to compare sizes.
Thank you.
All right. So number 9 says arrange P3 minus, Cl minus, K plus, and S2 minus in terms of increasing atomic radius. All right. So you guys better have atomic radius down after this because this is like our third problem with it. So increasing, once again, we're going to have small, big. All right. So let's draw out where these are again on the periodic table. So we have P3 minus. We have chlorine, which is going to be over here, chlorine minus. We have S2 minus in between them. And which am I missing? Potassium. Okay, so we have potassium down here. All right, so all of these are ions, right? And they're all isoelectronic to which other element?
Argon?
Yeah, argon.
Yes, they're all isoelectronic to argon. Okay, so we know since they're all isoelectronic, they all have the same amount of electrons once again. So now we want to compare protons. So whichever one has the most protons is going to be the one that can pull in those electrons the best. So they'll be the smallest. So which one has the most protons?
The chlorine?
Yeah.
Okay, close. Don't forget about potassium, right?
Oh, right. Yeah.
But yeah, we put potassium.
It'll be potassium. So we have potassium as the smallest, and then we'll have chlorine minus, sulfur 2 minus, and phosphorus minus. All right. Yeah. So this should be K plus Cl. Yeah, it should be C. Everyone good with that one?
Yeah. Could you remind me again why it's potassium again that goes first?
Potassium, because it has the most protons.
Oh, okay. Gotcha. Thank you.
So remember, like the more positive charges, pretend this is like the nucleus, right? The more of those that you have, the stronger it's going to be able to pull in that outside electron shell. So it'll have a smaller radius.
Gotcha. Thank you.
All right. So this one says, arrange the following species in order of increasing ionic radius. Okay, so don't get tripped up by this. It's the same thing as atomic radius. You're just working with ions, so sometimes he'll write that. So I'm gonna do the same thing here. Have F minus, P3 minus, sodium plus, magnesium 2 plus, and okay, hold on. I'm gonna have to move this phosphorus over. Okay. So you guys should know the trend by now. So what are we thinking? Which one? So we want increasing. So which one would be the smallest?
Aluminum 3.
Aluminum 3. Okay, perfect. Why? Why is it not?
Because it has the greatest amount of protons.
Okay, actually, so be careful. So it would be the smallest out of sodium, magnesium, and aluminum because it has the greatest protons and they have the same electrons. But don't forget that we have fluorine up here, right? So would fluorine be the smallest?
Yeah.
Yeah, fluorine would be the smallest.
Okay,
Or-
trick question, right? Okay, so all of these are isoelectronic. So fluorine, sodium, magnesium, aluminum, all of those are isoelectronic with neon.
Oh, okay. Is it
Got it?
phosphorus?
Phosphorus is actually going to be isoelectronic with something else. So these four are isoelectronic with neon. And then phosphorus is going to be isoelectronic with which element?
Argon?
Yes.
Argon.
Okay. So now we can compare neon and argon essentially, right? So these four have the same electrons as neon. So whichever one has the most protons is going to be the smallest. So that should be
Magnesium.
close.
Oh wait, aluminum. I didn't see.
Yeah,
Yes.
aluminum. Yeah.
Aluminum, perfect. Yes. So I couldn't see who was speaking at the beginning, but good job. Aluminum would be the smallest. And then we would go to magnesium, right? And then sodium, then fluorine. And finally, we would have P3 minus. So we know that argon is right under neon. So we know argon has to be bigger, right? Essentially argon but it's P3 minus. Okay, so let's see. Do they have it here? Yes, perfect. So the answer should be D. Okay. Any questions about that one?
No.
Number 11. For the following atom-atom bonds, which bond would be most polar? Okay. So polarity has to do with which trend? Which period?
Electronegativity?
Electronegativity. Yes. Electronegativity. Okay. So let's see. Which element is the most electronegative? You guys know?
Mm,
It's going to be fluorine.
Fluorine?
Yes, perfect. Fluorine. So usually the most polar will include fluorine. So if you look, let's see, let's look at NCl. So that one, we can't get rid of it just yet. We'll keep it in there for now. But if you look at the carbon-nitrogen bond for letter D, those are right next to each other on the periodic table, right? Carbon is number 6, nitrogen is number 7. They're super close to each other, so their differences in electronegativity are minuscule, like they're negligible, so they're not polar. Polarity has all to do with, it's all about a difference in electronegativity, right? Okay, so we're gonna cross this one out. Let's look at NF. Okay, so we have NF, we have BF and CF. So based on N, B, and C, which one do you think would be the most polar?
Boron?
Yes.
boron, yeah, boron.
So let's compare BF and NCl. Okay, so their distances look kind of comparable. I think if we like took a ruler, we would see that boron and fluorine like is a longer distance, but essentially what's gonna be the rule breaker here or tiebreaker here is that fluorine is the most electronegative element like ever. So if you see something far away from fluorine, did I say boron? Fluorine. Fluorine is the most electronegative. So if you see something bonded with fluorine that's like a good amount away from it, that's going to be a polar bond. Everyone good with that?
Yes, ma'am.
Cool. Okay, number 12 says, which of the following molecules is polar? All right, so we're gonna have to start drawing some structures here. So carbon tetrachloride. Okay, so what is the formula for that? Can anyone tell me? So we have carbon, right? So that's C.
Cl4?
Yes,
Yes.
CCl4.
Perfect. So tetra, that prefix means 4. So carbon tetrachloride is CCl4. How should we draw this molecule? Okay, so a rule of thumb is that the least electronegative is going to go in the center. So between carbon and chlorine, which one is least?
Carbon?
Carbon, yes.
Carbon.
So we're going to go ahead and draw, sorry, I'm like running out of room here. The 4 chlorines around carbon. Okay. So that is carbon tetrachloride. I'll try to get a different color for each. Methane. Does anyone remember the formula for methane?
CH4.
Perfect. CH4. So same thing here. We'll do C surrounded by 4 H's. Okay. Carbon dioxide.
CO2?
Mm-hmm. Okay. So I'm just gonna draw, yeah. Okay, so we're gonna have to go into valence electrons here. Should have done that from the beginning. Okay, so how many valence electrons does carbon have? Do you guys know how to find that?
It has 4.
It has 4, right? Yeah, because it's on group number 4. Okay, and then what about chlorine?
7.
7.
So we're gonna do 7 times 4 because we have 4 of them. So when we do that, we get 28 plus 4 is 32. So 32 valence electrons for this structure, right? And how many electrons are in a bond? So each of these lines is a bond, right? How many electrons are in there?
2.
2. So right now we have 2, 4, 6, 8 valence electrons. So we're just gonna put pairs all around. And usually elements like to have 8 valence electrons around them. I need to move this because I can't write on top of that. There we go. Okay. And then there are some specific ones that always have to have 8. Does anyone know which elements those are?
Gases.
Noble gases? Not quite. They're kind of in that area. Anyone want to take another guess?
They're right. Are they to the left of them?
They are to the left of that. Okay, so we have the octet rule. And this octet rule says that these elements can only have 8. They can't have any more, they can't have any less. So it's going to be for B, C, oh no, not B. Go back. C and O. Yeah. All right. So carbon, nitrogen, oxygen, fluorine always have to have 8, that exact number. But other elements can break that rule. Okay, so now that we put lone pairs, okay, another thing. What I just circled, how many lone pairs is that?
1,
1 lone pair.
How many lone pairs of electrons is it?
2.
Yes, perfect.
2.
So be careful with that. Each of these is an electron, but together they're just one pair. So that could also be a question. All right, so back to what we're doing. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So this is perfect. We have exactly 32 electrons around this structure. Okay, so we said carbon wants to have 4 valence electrons, and hydrogen, how many does hydrogen want?
2.
2, okay. Why do you say 2?
It wants to be helium.
Let's see helium. Oh, I see what you're saying. Okay, so it would like to be a noble gas, but like on the periodic table, if we're looking at like just hydrogen, how many
Oh,
electrons?
it's just 1. I'm
Just
sorry.
one?
Yeah,
Yeah.
it's just 1.
Yeah, no, don't worry. I probably worded that kind of weird. Okay, so we have 4 for carbon, and then we have 4 times 1 for hydrogen. So we get 8 valence electrons that we can work with. And we said that each of the bonds has 2. So we have 2, 4, 6, 8. So that's it. We're good to go. We can't add any more lone pair electrons, right? All right, so what about for carbon dioxide? We have 4 valence electrons for carbon, plus how many for oxygen? So we have 2 oxygens with how many electrons?
Six.
6.
6, yeah.
So 6 times 2 is 12 plus 4, 16 valence electrons. Okay, so how you can always start out is just draw 8 electrons around every single element that you have. And sometimes it works, like in the examples we had before, but sometimes it doesn't, and we're gonna have to make some changes. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so right now if we leave it like this, we have 20 electrons, right? But we can only have 16. So what should we do? Should we just erase some and call it a day?
Could we maybe use another bond?
Yes, we can start making double bonds. Okay, so when you make one double bond, you have to get rid of 2 lone pairs, one on each element, right? Because of the octet rule. Both carbon and oxygen follow that rule. So right now, if we leave it, carbon's gonna have 2, 4, 6, 8, 10, and it can't have that. Same for the oxygen over here, 2, 4, 6, 8, 10. So we erase 1 and 1. Oh, that erased in an awkward way. There you go. Okay, so let's count again. 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, so we still have an extra one. So let's add another bond. And that makes us erase. Oh my God, why is it erasing this way? That makes us erase 2 lone pairs, right? Let me add the carbon back. And now let's count them again. We have 2, 4, 6, 8, 10, 12, 14, 16. Okay, so we're good to go now, right?
Yeah.
So that is what the structure will look like for carbon dioxide. All right, does anyone remember the formula for ammonia?
NH3.
And yeah, NH3.
Perfect, NH3. All right, I'm just gonna come down here. We're gonna erase anyway. So let's draw NH3. How many valence electrons does nitrogen have?
5.
5? 1, 2, 3, 4, 5. Yes, perfect. And then we have 3 hydrogens. Each of them only has 1. So we got 8 valence electrons. All right, so right now if we count them with our bonds, we have 2, 4, 6. So we're gonna add some to nitrogen. Remember, nitrogen also follows that octet rule. So it should have 8, and now it does, so we're good to go. Okay, and finally, I'm running out of colors here. Let's do pink. Okay, so boron trifluoride. What is the formula for that one?
EF3. EF3.
EF3, perfect. Okay, so again, remember least electronegative in the center. So obviously boron, because fluorine is very electronegative. Okay, and then we're gonna get our valence electrons. So boron has how many?
3.
And we only have 1. And then we have 3 fluorines with how many valence electrons?
6.
7.
7, yes, 7. So that's 21 plus 3 is 24 valence electrons. Okay, so let's do what we did. We'll just add so that each of them has 8 and see if that works. Sorry, this one's kind of drawn over. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Hold on, I lost count. 2, 4, 6, 8 times 3, right? So 8 times 3 is 24, 26. Okay, yeah, so we have extra, right? So boron, let's think about this. We know fluorine has to follow the octet rule, right? But does boron have to follow the octet rule?
No.
So we can erase this lone pair up here. And we should be good. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Cool. So that is the structure for boron trifluoride. Okay, so now we can finally compare polarity. Okay, so which of the following molecules is polar? So we have carbon tetrachloride. Is there going to be polarity if we look at the structure? So there's 4 surrounding chlorine. And which one is more electronegative? Chlorine or carbon?
Chlorine.
Chlorine.
Chlorine, right? So chlorine's going to be pulling this way, it's going to be pulling this way, it's going to be pulling this way and this way away from carbon, right? Because it wants those electrons. So if we look at this, we can see that all the arrows cancel out, right? So that means that this molecule is not polar. Now the bonds are polar, right? All these bonds are polar, but they all cancel each other out. So the molecule in total is not polar. Okay, carbon and hydrogen, there's like a very small polarity here, and it would be the same thing. They would cancel out, right? Because we have 4. So we know it's not carbon tetrachloride, we know it's not methane. Let's look at carbon dioxide. So which one is more polar, carbon or oxygen? Or which one has a stronger, is more electronegative?
Oxygen.
Oxygen.
Oxygen. So it's going to be pulling this way and this way away from carbon. But again, what happens? They cancel out, right? So carbon dioxide is not a polar molecule. Let's look at ammonia. Okay. What do we think here? Which one is more electronegative?
Nitrogen.
Yes,
Yeah,
nitrogen.
hydrogen.
It's going to be nitrogen. So they're going to be pulling this way towards nitrogen. And once we go, I know he said that some of the geometry questions are going to be extra credit. But if you look at the nitrogen of ammonia, it's going to kind of look like a pyramid, right? It's going to have those 3 H's on the bottom and the nitrogen and then that lone pair on top. So all that pool is going to be like going up. So we call it like an overall dipole. And it's going to be like this because all those H's, they're going to kind of look like how it looks down here, right? The 3 H's instead of 4. And then the lone pair up here. And the dipole is going to be going up towards that nitrogen. So this is a polar molecule. And then we can look at boron trifluoride. Again, that would kind of look like a pyramid, but they would all be going towards fluorine, right? And that would balance each other out. Okay. That one's a little more like, I don't know how far you all got in lecture, but do you guys have questions about that one?
Yeah.
Okay, what's up?
Generally speaking, like the one that's in the middle is least electronegative, right?
Yes, except when we have hydrogens, that's kind of like the one place where that rule doesn't work because hydrogens just tend to be on the end because they can't bond with anything else, right? They only have that one valence electron. So we can't like add things on like all 4 sides of it.
Gotcha. That makes sense.
All right, any other questions? Okay, so I have time for one more and then I'll hand it over to Diego. Okay, of the following solids, which would have the greatest lattice energy? Okay, so this is just like the one we did earlier, right? We have potassium with its +1, iodine -1, lithium +1, -1, Mg has a 2+, this has a -1, calcium has 2+, -2, +2, -1. Okay, so right away we know we can cross these out. Okay, but what do we do from here? So calcium and bromine and magnesium and chlorine are kind of an easy comparison, right? But then we have calcium and oxygen. And you can see that oxygen has that greater charge, right? Oxygen has that greater charge, and it's also more electronegative than chlorine and bromine, right? It's closer to fluorine. So that means that it's gonna pull those electrons right? It's gonna have more affinity for electrons. So which one do you think would have the greatest lattice energy?
Wouldn't it be CaO?
Yeah. Okay, so that is that one. I am going to have to run off now. So Diego can answer any questions you all have. Good luck on your exam tomorrow. I'm sure you all will do great. And yeah. Let me stop sharing my screen.
All right, cool. Oh, we lost some people in the process. All right, bye, Paulina. Take care. All right, so I will take up after. Wow, I just noticed that in this practice review that he gave you guys, there's not really any questions on electron configuration or quantum numbers. Let me see if his review session or the review that he has on Blackboard has any. Is there any questions, by the way, before we start? Any questions that or material specific topics or questions you want me to go over?
I'm kind of a little bit confused on atomic radius and ionization energy.
On atomic radius and ionization energy. Okay. So, okay. Awesome. Cool. I can help you with that. My notes. I don't screw up because that is a big no-no as a peer leader. Okay. So I'm going to share a whiteboard. So ionization and atomic radius, correct? So atomic radius, we'll go over this one first. And then I'm going to draw a very poor representation of our periodic table. I already messed up. Okay, there's hydrogen, middle. I don't know why I made hydrogen so massive. Okay, so what's the general trend that we do whenever we have atomic radius? How does it increase?
Downward?
I'm sorry?
Downwards?
Yeah, we increase going downwards, so we increase. And then how do we increase horizontally?
Going to our left?
Yeah, going to
To
the
the
left.
left.
Yes. So to the left and down. That's the general trend that we have. So what decreases as we go from left to right? Or sorry, not left to right, right to left. What changes? So we can take the example of fluorine to lithium. What changes as we go across?
The protons.
There's less.
I'm sorry? You were on, you said something, Noel.
I was agreeing with Alyssa, the number of protons.
Yeah, right. A number of protons, and then what else decreases as we go? So number of protons decrease. That's one thing. What else? What else changes?
The valence electrons and the atomic mass.
So you're correct about, I wouldn't say atomic mass plays a part of it. It's more so that the electrons do play a part.
Oh, the electronegativity?
Not exactly. Electronegativity doesn't affect doesn't affect the radius as much. But it is the electrons. We decrease in the number of electrons, right? So when we compare lithium has 3 electrons, while fluorine has 7 electrons. So our electrons decrease as well. I'm trying to increase that. Electrons decrease. So because of this decrease, our radius increases. Okay, now what's changing when we go from top to bottom? Why does the radius increase? What's changing? What's the
Oh,
difference between lithium and cesium?
the shells, like the energy
Yes.
of the shells.
Yeah, we're adding more shells, right? So addition of shells. So with the addition of shells, our radius increases. Did that sort of clear up how atomic radius works? Is there any other questions about atomic radius?
No. So
No.
it's basically increasing when you're going like from right to left and then down.
Yeah. Another important thing that if you are continuing, or if you're a chem major mostly though, I would still say understand what shielding is. Does anyone know what shielding is?
Does that have to do with the shells being able to shield the electrons that are on the outside?
Yeah, it does have to do with that. So basically what happens is that, yeah, the electrons shield the positive charge of the positive charge of the nucleus. So that's why the valence electrons don't really experience much of the charge. The core electrons do. So electrons shield, kind of like basically shielding. So shield the nucleus, the other electrons from positive charge. So which subshell do you guys think has the highest shielding?
The F?
Actually, no. The s orbital. F is the worst, actually. So shielding decreases as you change orbitals. So the s orbital is much better than the p. The p orbital is much better than the d, and the d orbital is much better than the f. So your s will always have the best shielding. So if we change this instead of increasing, so if we change this up, and then if we do it this way, so decreasing, so it decreases going from left to right and decreases as it goes from bottom to top. This is our radius, by the way. What's the difference between the L and the F in terms of subshells? So looking at our electron configuration of lithium, what's our electronic configuration of lithium?
One S2,
Mm-hmm.
One.
one.
2s1, yes.
Yeah,
And
two
then,
is one.
and then what about fluorine?
One S2, two S2, two P5.
Yep, you're correct, 2p5. All right. What's the difference between the electron configuration? Other than the difference in electrons?
The Li doesn't have a p orbital. It just has s and it just has s.
Yeah, you're correct. Yeah. So lithium only has an s orbital, while fluorine has a p orbital. So shielding decreases as you change subshells. So basically, our atomic radius decreases because our shielding decreases. Does that make sense?
Yes.
All right.
Yeah.
So that's in regards to that. Other than that, I don't really think there's much else to atomic radius. Yeah. Now, before we go on, let's go ahead and do ionization. So I'm gonna clear it real quick. So ionization. So for ionization, what is ionization energy? What's the definition?
Ability to remove an electron.
Yeah.
Energy needed to remove an electron.
There you go. Energy needed to remove electron. So the energy needed to remove an electron. And then when looking at our periodic table, how does the trend look? What way does it increase?
To the right.
Yeah, it goes up and to the right.
Yes, up and to the right. So it increases going up and it increases going to the right. So why does it increase going from left to right? If you guys understand why it increases, you'll be perfectly fine for any questions thrown at you.
Does it have to do with how close they are to the noble gases?
No, it doesn't.
Or the size of their atomic radius?
It does deal with size. It does deal with the size. But what is, going back to shielding,
Oh, they have more electrons towards the right, right?
there's more electrons. We have an increase in electrons. And then what else do you guys think contributes to the increase in ionization energy? So let's go ahead and use lithium again and then fluorine again as our examples. So lithium, you guys given me 1s2, 2s1, and fluorine also has 1s2, 2s2, 2p5. So other than the change in electrons, what else?
The shell.
Yeah, the shell, right? We have a different shell. We have P. So a decrease in shielding. What do you think that if the electrons are less able to shield the positive charge, how do you think the protons are interacting with the electrons?
Stronger pull.
Yeah, a stronger pull, right? So you're going to need a lot more energy to pull those electrons away. So shielding decreases. There's also another term that I recommend that you guys get familiar with is effective nuclear charge.
That's the amount of protons, right? In the nucleus.
I'm not entirely sure. To be honest, I completely got stumped whenever we went over effective nuclear charge. But it does deal with the protons and electrons. It's essentially, the way to think about it is how the valence shells experience the positive charge of the protons. So effective nuclear charge. So typically, effective nuclear charge increases. So shielding increases effective nuclear charge. So the electrons have more. The protons have more of of a hold on the electrons. So that's basically what effective nuclear charge. So effective nuclear charge increases as well. And then going from bottom up, so why does it increase going up a group? So bottom up, what changes? So going from cesium to lithium.
The shells.
Yeah, it does deal with the shells. So our shells decrease. And if our shells decrease, how does that look for our electrons and our protons?
Is there stronger attraction between
Yeah,
them?
shells decrease, therefore stronger proton and electron pull. So when looking at, I think a good example was the beryllium one. So beryllium, our first ionization energy, I don't have it memorized, but comparing our first ionization to our second ionization. So we already pulled one electron and then we're going to pull another one. Are we going to require more or less energy? So here's beryllium. Here's my 2 electrons. So let's say I already pulled one and now I want to pull this one. Is my ionization energy going to be higher or lower than my first? Let's say this one's 10 kilojoules. What do you guys think?
Wouldn't it be lower?
Think about it in terms of protons. So we have in our first initially we have 4 protons and 4 electrons. That's ground state. And then we pulled 1 electron. So we have 4 protons, 3 electrons. If I want to pull another electron, how do you think that interaction is going to look like?
It's gonna be more difficult.
Yeah, it's going to be a lot more difficult to pull it away now, right? Because I mean, you have 4 protons, you got 3 little electrons. I mean, it's a 4v3. It's kind of lost battle. So if you want to pull another electron away, you're going to need even more energy. So the second ionization will be much larger. And that's typically how the trend goes. It increases in ionization. Because we're going from beryllium to beryllium +1 to beryllium +2. Is there any questions? I hope I didn't confuse you further. Everyone good?
Yeah, I think I'm good.
Never thought of it in terms of shells, but it makes sense.
Yeah, I typically think about it on that, but typically I also just look at the periodic table and then like, oh, this one seems higher than this one, so that's how I typically go about it. All right, so there's no more questions. Let me go see. Okay. In chat, do you guys want more, or how's everyone feeling about quantum numbers and electron configuration? Everyone got a handle on them? Or would
Can we
you
go
like
over quantum numbers and electron configuration?
Sure. All right, no worries. It's good. Let me go ahead and clear it. It's because Dr. Saupe's practice exam doesn't exactly have, a lot of it is on structures, and I don't think that has a heavy emphasis on the exam. Yeah, I don't think it's, all right. We're gonna have to go Just pull up one of my old worksheets then. What module is quantum numbers, by the way? Is it module 10? Nope, it's module 11. Ah, shoot. Okay, let me open my Word document so we can do some problems. How are you guys feeling with this exam? Does knowing that the exam will really hurt you kind of ease your nerves?
Yeah, a little bit.
That's good. Yeah, that's good. Typically, students get a little nervous around the fourth exam, but I think it's nice that he is letting you guys take an option of taking it or not. All right. This is not very. Yeah, we'll try our best. So here I'm asking you guys to do the electron configuration, the quantum numbers, and the box diagrams. So how many of you guys are familiar with using your periodic table for doing the electron configuration? Or how many of you guys use your periodic table?
I definitely do.
Okay.
Yeah, me too.
Okay,
Same.
so you guys are used to using the periodic table. I'm going to show you a method I prefer to use. In my opinion, it's much easier. So the method is you have to draw it out. Unfortunately, that's the one downside. How many levels? How many S subshells is there?
7.
7. So 4, 5, 6, 7. So we have 1, 2, 3, 4, 5, 6, and 7. Then how many p levels is there? Yeah, 6. So P, that is 6. So it starts at 2, 3, 4, 5, 6, and 7. And then how many D subshells is there? And what number does it start at?
There's 4.
4.
And what number does it start at?
3.
And F? And then what level does it start at? F is that bottom row.
Is it
So,
4?
it's 2. It starts at 4, yes. It starts at 4 and ends at 5. So there's 2. Okay. So the way it goes, so there's 2 electrons, the S subshell. There's 6 electrons here. How many does the d orbital hold?
10.
10.
And the F?
14.
Yeah, 14.
Yeah, 14.
There you go. Okay, so let's do sodium to start us off. So how many ground state sodium, how many electrons does ground state have? Electrons total.
11.
11 electrons. So the way you use this little table you just drew up, and honestly, it's not that organized, and it's not my best table, but hopefully you guys understand. So you go from top right to bottom left. That's how the trends go. So that's 1s2. How many electrons do I have accounted for already?
2.
Yeah, 2 electrons, right? 2s2. How many is that already?
4.
4 electrons.
4.
2p6. How many is that already that I counted for? 10. Yeah, 10.
10, yeah.
10. And then 3s. And then how many electrons do I need out of 3s?
just one.
Yeah, 1, right? Because if I do 3s2, how many electrons total does that make?
12.
Yeah, that makes 12,
12.
and we need 11, right? So -1. So there's your electronic configuration for sodium. Yeah, pretty simple, right?
Oh yeah.
Much easier than having to look at the periodic table and like having to remember like, oh shoot, 4s. And it works also for, because as you guys go further down, like for copper, you guys have to go into the d orbital and it gets weird. But we'll do. Okay, and then but the question is asking for sodium 1. So Na, yeah, Na. So for the sodium ion, what is my electron configuration? Actually, I'll just make it here. How many electrons does the sodium ion have?
Oh, it's gonna lose one.
Yeah, it's gonna lose 1.
Yeah.
So it'll be 10. And so what I have to change about my electronic configuration?
Take one from the S.
Yep. So there it is. So now we have just an empty s orbital. It's S0. That's not proper though. It's that this would be proper. But just know that there's an empty s orbital right there. Okay. But this would be what you're looking for. Okay. So we have that. And then our quantum numbers. I don't really like the ions, to be honest. Quantum numbers for ions don't really work. So we won't worry about that for ions. So we'll go back to the regular old sodium. So for our quantum numbers for sodium, out of what set of electrons do we base it on?
The last set.
Yeah, the last set, right?
The last set.
We base it on this last set. We are 3s1. So what are my 4 quantum numbers?
Your N is 3.
Mm-hmm.
Your L is 0.
Mm-hmm. And before you answer ML and MS, how does my orbital box diagram look like?
Oh, it's just one box.
Yeah, just 1 box, and that's 0. And then how do I go my electrons?
Facing up for the first one.
And yeah, am I done?
Yeah,
Okay. And then so what's my ML?
it'll be 0,
Mm-hmm.
and then it'll be positive half spin.
Yes, positive 1. There you go. Awesome. All right. Any questions on the sodium?
Where did you get the zeros and the plus half?
Okay. So this 0, so the way it goes is that if you have L 0, 1, 2, 3, and 0 will always be s orbital. L1 will be p, 2 will be d, and 3 will be f.
Oh, okay.
So what was my what was my orbital here in my last electron pair?
3s1, so it's S.
S. So what will be my L quantum number?
So it'd be 0.
And then during my box diagram, so for S, since my L is 0, oh sorry. Yeah. So for S, this is my L will be equal to 0. What are my possible values for ML?
Negative and positive half.
That's MS. That's MS. ML.
Oh, MS. My bad.
ML. What would be my values for ML?
-1, 0, and 1.
Is my L 1?
Oh no, it's 0.
Yeah, so my ML will be 0. Now for my P, so my L is 1. What are my possible values for ML?
It would be -1, 0, and 1.
And then D, sorry, that's P. So D. What is the value for L?
It would be 2.
It'll be 2. And then what are my possible values for ML?
-2, 0, and 2.
-2. It's the range from -2 to 2.
Oh,
So
yeah,
negative
1.
2,
Yeah.
-1, 0, 1, and 2. And then, so the orbital box diagram for S will be just one box. The orbital box diagram for P will be 3 boxes because we have 3 possible values for ML. And then how many boxes will we have for L, for D?
5.
5. There you go. There you go. That is your orbital box diagrams. Any questions on that part?
No, now I get it.
Okay, cool. All right. So I'm gonna go ahead and erase that. I'm gonna scroll down a bit. Just enough so you can see that portion. Okay, so I'm gonna erase this. Go with this space. Okay, and then MS is the last value. So MS comes from our electrons. So here we have only one upward electron. The way we fill our orbital box diagrams is we do up electrons, positive electrons going up, and negative spin going down. And then whatever your last electron, the last electron you placed is, the orientation of it, that is, will determine your spin. So since we only have one and it's upward, it's positive 1.
Oh, okay.
We'll do a couple of more examples that way you guys kind of get an understanding of that. I will leave sodium up here though. Okay. Let's go ahead and do bromine. Yeah, let's do bromine. So unfortunately, I will make you write the whole electron configuration of shortcuts. You guys don't get an easy pass. I need to know that you guys are good. So how do I start by, do you guys prefer periodic table or do you guys prefer this graph table?
No, that method better.
Okay, how many electrons does bromine have?
$35.
35, yeah.
Sorry, I made him check. Okay, 35. So how many electrons have I counted for there? That's 2 electrons. These are 2. So 2 electrons. I have 33 more to go. So, oh no, that's erasing it. 2s2. There you go. All right. 2s2. That's 4 electrons. 2p6 and 3s2. That's 8 electrons. I'm losing count. I don't know when to stop. 3p6. How many electrons have I counted for already? 6, 12. I'm sorry?
18?
Okay,
18,
18
yeah,
electrons
18.
so far. All right, I still got a bit to go. All right, 2s2, that's 20. 4s2, dang it, I have to go underneath. 3d10, that's 10 more, so it's 20, 30. So 3d10, and then 4p6, right? That's my electron configuration. Right, this all equals up to 35.
It equals 36.
It equals 36. How many does it do? How many does the erase from this last one?
Just 1.
Yeah, just 1. So 5. There you go. And of course, the shortcut is much easier How do we do for shortcuts? What do we base it off of?
Argon core.
Yeah, argon. We go based off our last noble gas. So
Yeah.
argon takes up until 3p6, and then we just have 4s2, 3d10, 4p5. There you go. That is your electron configuration. All right, and then looking at our quantum numbers, so N, L, ML, and then MS. So what do we base our quantum numbers off? Do I base them off on my 3d10 electron?
Your last one.
No, on the last one.
Yeah, base them off of my last one, right? So 4p. So 4p5, this will be my focus. So what's my N?
4.
My L?
1.
1.
1.
There you go. And then what, how many, before we start assigning ML and MS, how many orbital box diagram? How many orbital boxes will I have?
3.
3. Yes. So I'll have 3 boxes. And then what are the values of the boxes?
-1, 0, +1.
There you go. Awesome. Okay. And then how many electrons do I have?
5.
5. We go
5.
based off our exponent. And how do we fill it?
So you start by putting 1 in first, and then you just go from there.
Yeah, we kind of put up arrows and then down arrows. And then there's 5. So the last one, I placed it on 0. So 0 is my ML. And then what's my MS?
-1/2.
-1/2.
-1/2.
How do I know it's -1/2?
It's pointing downwards.
Yeah,
Yeah,
the
it's
last
pointing down.
the last electron we placed had a downward spin. So it's -1/2. There you go. No, that's 0. There you go. That is your electron configuration. Any question?
No.
Everyone Gucci?
Yes.
Yeah.
Awesome. All right, so let's go ahead and do copper. So what's special about copper? Well, actually, it is relevant. So, so for copper, my electron configuration, how many electrons does copper have?
29.
29 electrons,
29.
yes, 29 electrons. All right, so there's 29 electrons I have to account for, so I'm gonna go ahead and do the shortcut method because it takes forever to do the other method. So AR, and then how do I continue it after argon?
So it'd be 4s2.
Yeah, 4s2.
Then 3d9.
Yeah, 3D. But
Yeah,
copper
3d9.
is special. What's special about copper?
Oh, can it like borrow an electron from the S shell to complete
Yeah.
its Saupe?
It can. It is very close to having a full D shell. So what happens is that it pulls it from the D shell and leaves 4s alone. It takes 1 electron from 4s and transfers it. So yeah, this is your corrected copper equation. It is an exception. Okay. Okay. And then how will our quantum numbers look like? N, L, ML, and MS.
N would be 3.
N would be 3. What's my L?
2.
Yes, 2. And then how many boxes would I have?
It would have 5.
Yes, I'd have 5. So 5 boxes. 1, 2, 3, 4, 5. Okay. And then what are the values of the boxes?
-2, -1, 0, +1, +2.
Mhm. Okay. And then, so how many electrons would I have?
10.
Yes, it would be 10. So so it will completely fill its d orbital. Okay. So we have +2. And then what's the spin of the last one?
-½
Yeah, negative.
Yes, -1/2. There you go. Okay. Any questions?
No, it's pretty simple.
All right, cool. And then the last one, which is chlorine. And I think that'll wrap up quantum numbers and electron configuration for now. Hop back up to doing molecules. For chlorine, what is the closest noble gas to chlorine?
Neon.
Neon.
So neon. And then you guys tell me the rest.
(3s2) and 3p5.
There you go. All right. Then N, L, ML, MS. So what is my L? My
Your
N.
N
So,
would be 3.
1 for your L.
and then how many boxes?
3.
3.
Yeah, we'll have 3 boxes. And what values would you have?
-1, 0, and 1.
And then how will I fill the electrons?
Starting facing up.
Facing up first.
Down. Okay. And then so what is the position of the last electron?
0.
0. And then my MS value?
-½
Negative. Yes. -1/2. Awesome. You guys did well. And then hopefully you guys can, hopefully this helped you out. Yeah. All right. Let's save it just in case. All right. Any questions? Quantum numbers.
No.
Okay. Everyone good. All right. So let me go ahead and stop sharing. All right. So I'll close that up. All right. Back into problems, practice problems for Dr. Saupe. Okay. So for this, I believe Paulina stopped here at problem 14. So for problem 14, the molecule drawn, and then, so this is a weird one because you kind of have to look at the molecule. First of all, which molecule is this? It's one we kind of need to live on.
H2O.
Yep, H2O.
H2O.
Yeah. By the way, have you guys do you guys know how to determine molecular geometry? Have you guys gone over that in class?
No, we didn't go over geometry in class. He didn't say it would be on the test from what I could
Yeah,
remember.
I don't think he's gone over it because he says it's not really important because it was not gonna be on the test.
Okay. All right. All right. That. Yeah. All right. It might be a bit difficult then to explain this one. Um, well, not completely difficult, but we'll go ahead. I'll try my best. So, first of all, what do these arrows represent? First of all, what does this arrow mean? Paulina kind of used it in problem 12.
Does that have to do with like the force, like pulling?
It has to deal with if it's polar or not. It's a dipole moment. And it kind of tells us in which directions the atoms are being pulled. So it helps determine if we have polar bonds. That says ponds, not bonds. Polar bonds. So that's a dipole moment. So in this dipole moment, what is the hydrogen doing to the oxygen? Or what is the oxygen doing to the hydrogen? Sorry.
Pulling it towards it?
Yeah,
Yeah,
it's
it's
pulling
pulling it
towards
towards
itself,
it.
right? So out of these answers, which one can we eliminate? What if we have these arrows, what does that tell us? What type of bonds are they?
Polar bond?
Yeah, these are polar bonds. Okay.
So I have a question. So
ahead.
it's a polar bond if it's being pulled one way instead of the other? Like,
Polar bond deals with the difference in electronegativity.
okay.
Basically, the more electronegative the element is, if a really electronegative element is bonded to a really like an electropositive element, something
Yeah.
that's doesn't really have not high in electronegativity, that electronegative element will pull it towards itself.
Oh, okay.
Essentially.
So it's just a difference in electronegativity between the.
Yeah. So the difference in electronegativity causes that dipole moment. It causes that molecule to be pulled towards itself.
Gotcha. Thank you.
So here we have polar bonds. So which one do we have nonpolar and polar bonds? Is there
No,
any
we just have
nonpolar
polar
bonds?
bonds.
No, just polar bonds, right? So we can eliminate C already. Do the polar bonds cancel each other?
No.
No. How do we know that? So it may be difficult to answer. So oxygen has a weird, it has a bent molecular geometry. That's the molecular geometry. And it pulls the hydrogens towards itself. So overall, there's one big dipole moment being made here. Is there anything, is there like another dipole moment going downwards to cancel that out?
No.
No, right? So there's nothing there to cancel it out. So that's how we know. And I'll go over, actually, I'll show you guys an example where it looks like it should have one, but it isn't. Okay, so they don't exactly cancel out, right? They're kind of, they create a big dipole moment. All right. And then is this molecule nonpolar then?
No.
No, right? And then so we left with D and E. So E is kind of hard to answer because you guys kind of have to know how to go about assigning molecular geometry. So in the back of your book, or your workbook, there's this big table. It's right behind the periodic table. Normally, you guys have to memorize that whole table. But Dr. Saupe is, since he hasn't been able to go over all the material, you guys don't really have to memorize it. But I really highly encourage you guys to memorize it and kind of learn how to use it and how to use the information on there, because it will come up in Chem 2. How many of you guys have to take Chem 2?
Yep, that's
I
me.
do. I
Yeah.
have to take it.
Chem 2 does have you guys kind of go over how to assign molecular geometry and electronic geometry. So I kind of recommend going over it. It's pretty important, especially if you're a chem major or bio major. Oh, not bio, sorry. Biochem major. So the way we assign, so I'm gonna quickly go over it. It's not gonna be as full in depth as I wanted to, but how many bonded regions do we have? How many bonds do we have?
2.
2.
2 regions, okay. And then how many lone pairs do we have?
2.
2.
Okay, so here's our 2 bonded regions, and here's our 2 lone pairs. So in your graph, which line, what is the molecular geometry when you have 2 bonded regions and 2 lone pairs? What is my molecular geometry?
Tetrahedral.
That's my electronic geometry.
Oh, bent.
Yes, bent. So my molecular geometry is bent. And why do you guys think it's bent?
Because the hydrogens, there's only 2 of them. Oh, yeah.
No, go ahead.
No, I was just gonna say because the hydrogens are just pulling on one side of the.
Not essentially. So the reason why it's bent, it deals mostly with these lone pairs and these and the hydrogens. So it does have to deal with the hydrogens, but it also deals with the lone pairs. The lone pairs kind of push it down. The lone pairs don't really like to be underneath here. That's incorrect. So the lone pairs kind of push down the hydrogens to the side and make it into a bent shape. So hence why it's bent. So now that you sort of assigned the molecular geometry, has a tetrahedral molecular geometry, is that correct?
Yeah.
Well, it has a tetrahedral electronic geometry.
It doesn't make sense. That's electronic geometry.
Electronic geometry is tetrahedral, but it's asking about molecular. So is our molecular tetrahedral? No, it isn't.
It wouldn't be it.
No, because molecular geometry is actually bent. It's not tetrahedral. So our only option has polar bonds and the molecule is polar. That is correct. We have polar bonds and we have nothing canceling out, so therefore it's a polar molecule. Whew. Gosh. Yeah. Thankfully, it's not that enforced throughout the exam, but I highly recommend that you guys sort of get familiar with it. The graph isn't too hard to work, in my opinion. It's mostly just look at what you have and then match. But yeah. Okay. Shoot. Actually, let me go over that one example I wanted to go over. So BF3. So boron trifluoride. Actually, hold on. I'm gonna try how you guys can draw this. So how many valence electrons does boron trifluoride have? We'll go about in the Lewis structure. Boron has 3 valence electrons. Then how many valence electrons does fluorine have?
7.
7 times 3. So how many total?
Wouldn't it be 24? Because it's 7 times 3 is 21 plus 3 is 24.
24. There you go. All right. And then which one would be my center atom? Once I start drawing it.
Boron.
Boron. And then we'll do our skeleton. So actually, I'm already drawing it how I normally draw it. We'll draw our skeleton. So fluorine, fluorine, fluorine. Okay. So how many electrons have I already used up making those bonds?
6.
6.
All right. And then, so I have 6. How many do I have left to use? 18. So we'll assign those 18 to our fluorines. 2, 3, 4, 5, 6, 12, 14, 15, 16, 17, 18. Okay. And then you guys can check your formal charge, but this is the stable structure of boron. So, or do you guys want me to go over formal charge with you guys?
Could you go over formal charge as well?
Yeah, can you go over it?
Formal charge. So what's my what's the equation for formal charge, by the way?
Formal charge equals the number of valence electrons minus half of electrons in bonding pairs plus half of electrons in lone pairs.
So half of the electrons in bonding pairs minus half of the electrons. That's a jumble. So the way I typically go about it is how many bonds do we have, and then plus the number of lone pair electrons we have. So I'll go and explain. So how many valence electrons does boron have, or is supposed to have?
3.
3. And then how many bonds do we have?
3.
3.
Yeah, 3. And then do I have any lone pairs?
No.
No.
My lone pairs is 0. So what's my formal charge?
Zero.
Yeah, 0. And then fluorine. So how many valence electrons does fluorine supposed to have?
7.
And then how many bonds does fluorine have? We're looking at only at one fluorine atom.
1.
It'd be 1.
One bond. And then how many lone pair electrons do I have?
3.
3.
That's lone pairs, but lone pair electrons.
Yeah, 6.
Yeah, there you go, Noah. All right, 6. You got it. Yeah, 6. 1, 2, 3, 4, 5, 6. So we have 6. So what's my formal charge?
0.
0.
That means the formal charge of all these fluorines is 0, 0, 0, and 0. Okay. Now, looking at your periodic trends, who's more electronegative, boron or fluorine?
Fluorine is more.
Fluorine.
So what is the fluorine gonna do to the boron?
Say?
What is the fluorine gonna do to the boron? Is it gonna push it away? Is it gonna pull it in? Is it gonna hug it?
Probably gonna push it.
It's gonna.
Remember electronegativity. It's the ability to attract electrons.
Isn't it
So,
gonna attract?
Oh, it's gonna pull it. Yeah.
yeah,
It's
it's
gonna pull it.
It's gonna pull it towards itself. So looking solely at this structure, is this molecule polar or non-polar?
Non-polar.
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 You guys answered correctly. The molecule is nonpolar. But why is it nonpolar?
Because it's pushing away from each other instead of attracting.
Not necessarily.
Mm.
These two are canceling out each other. But who's canceling out this one?
Nothing's canceling that one out. Okay.
No.
Not that one. So
Yes, but still, the molecule is nonpolar. And let me explain why. Looking at your little table, so how many bonded regions do we have on our central atom? How many bonded regions does this molecule
3.
have?
oh,
That's
3.
1, 2. It helps if you circle it. So we have 3 bonded regions. Do we have any lone pairs?
Yeah. No.
No, we don't.
No,
We don't have any lone pairs. So now, looking at your table, what should be my molecular geometry? Molecular, not electronic.
Triangular planar.
There you go. Triangular planar. So triangular planar. Okay. Triangular planar kind of says how it is. It looks like a triangle. It looks like a dorito. So boron is going to have a triangular planar structure. Now, if I draw my dipole moments, you guys see how they all kind of cancel each other out?
Yeah.
Yes. Yeah.
So this molecule is nonpolar because of its because of its molecular geometry. So in cases like that, it's important to know what molecular geometry is. But I am sure Dr. Saupe will be making these types of questions extra credit. Hopefully you guys are able to score them. But yeah. Okay, it is 6:30, so technically we are done. You guys are free to go. Not that you guys were obligated to come. But if you have any questions or any questions for me, I'll stay here for a little bit. Actually, I have to stay here until the other period leaders leave. But I'll stay here a little bit and see if you guys have any questions. So
Could you do bond stability and resonance?
sure. So bond stability, I haven't picked that before. But I do know resonance. Give me 1 minute. Oh.
I guess resonance.
Yeah, I don't know I don't know if bonds. Yeah, I can explain what bond stability is. It's
Okay.
yeah, it's nothing too big. Yeah, let me go. Let me stop sharing. Okay. Actually, I'll stop the.